Okay, I'm audible. So let's start. So my screen is visible, right?
Yes, sir, visible.
Okay, so we're going to start with this problem. So this is the first problem of today's division 2. And in this problem, we are given that we have a string S, and if one or more than one, some positive number of right parentheses appear between two columns, we say that it's a smiley. So we have to finally count the number of Schrodinger Smiley in the string S, which occur as a substring. So there are actually many ways to do this, but the easiest way is, let me just give me a minute. Okay. Let me save this. Okay. Okay. So we are given that a smiley is something which has some positive number of right parentheses between two colons, right? And we have to find total number of smileys that are appearing as a substring in string S. So what we can do, see, if there are two columns that are appearing like this, so instead of having them as twice, I can simply count them as one time, right? Is this making sense? There is no benefit for me to have these. Like, I can compress a string which is given to me like this. I can basically compress this as, I'll write this as once, this as these three as one, these three opening bracket or closing brackets as once closing bracket. Then I'll write this. Then instead of these three, I'll just have one character included in my, let's say this is some string S, this is some string X. And for these three, I'll again just write another colon and this. So this string and this string is going to have the same number of smileys. Is this clear? Because we are looking at substrings, right? If this is one smiley, I'm getting this smiley here. So if this is clear, first of all, is this clear that both of these strings will have same number of smileys?
Yes, sir, it's clear.
Okay, so now how to actually count the number of smileys? We just need to check three consecutive characters in this string X, and if the first one is a colon, second one is a right bracket character or right parenthesis, and the third one is a colon again, we'll say that we have a smiley. So we'll increment by answer by 1, and we are only going from 0 to, let's say, n-2. So our final maybe n-2 or n-3. So since we are going only these, we are only doing these operations, and for each index we are only checking 3 characters. So our implementation is O of n. We go O of n, right? So is this clear, or anybody wants me to explain this a little more, or is it's clear? You can implement this problem in many ways, so that's why I'm not wasting time on this problem. But if it's still, if someone is having any doubt, let me know.
Clear, sir.
Okay, so let's look at the implementation. So this is the implementation. In this, I'm first taking n as input, then string s as input. So initially, my string x is just an empty string, and I'm trying to build this string x from my string s. So I'll just include the first character of string s as it is in my string X, and then for all the remaining characters, I'm just checking if this character is same as the last character that was included in X, then I'll skip it. Otherwise, I'll include it in my string X. Finally, the count is the number of smileys that I'm getting. And if my X dot size is less than 3, this means that I don't have any of these smileys in my string S or X. So I'll simply output 0 and I'll continue. In this case, I'll return because these functions were implemented differently. Like this is another function, and I think if are there test cases for this problem? Yes, there are test cases. So I'm going to the main function. I'm returning to the main function, and then I'll again call this function for next test case. But if this is not true, then what I'm doing, I'm going from from starting from 0th index to this last index. This is x dot size minus 3. And for each of these indices, I'm checking if my current index is a colon. Next index has a right bracket sequence, and the I plus 2, that is the index which is next to next in position from current index. If it's a colon, then I'll increment my count, and finally I'm printing this count value. So is this clear?
Yes, sir, clear.
Okay, so let's move to the next problem. So, okay, let's first discuss this problem. So in this problem, we are given that we have an array A of size n, and a triplet array is defined as a collection of minimum of AI, AJ, AK, and we are finally given Q queries, and we have to output, okay, what is the kth smallest element in the triplet array? Also, K is between 1, and this is NC3. These are the total number of pairs that I can have. NC3 is nothing but the number of ways you can select 3 integers, or 3, if you're given n balls, the number of ways that you can select 3 balls out of those n balls is NC3. So how many people were able to solve this problem during the contest? Okay, so see, in this problem, we are given that we will have for each I less than j less than k, a triplet value is minimum of AI, AJ, and AK, right? So using this, we'll get, since number of ways to select I, J, and K such that this thing holds, we can select any of 3 values as 3 indices from our out of n indices, making sure that none of the two, like we don't select an index twice. So total number of ways for doing that is NC3. So that we cannot actually iterate over our array. Like we cannot iterate it over 3 times using n cube complexity and just try to generate these triplet array values. But what we can do is we can first of all sort our array, and then see each value will come some number of times. If we, let's say if I have 3, 1, 5, so how many times this, if you have this, you can count how many times this value will appear in your final triplet array, right? You can count, let's say this occurs x times, this occurs y times, this occurs z time. So or finally we'll have something like 1, 1, 1. If I write all the triplet array values in sorted order, we'll have something like this occurs x times, my 3 occurs y times, and my 5 occurs, okay, this is z, and this occurs y times, right? So if we just know how many times each of these values is going to appear in my final triplet array, that's more than sufficient for me to find which is the kth smallest value. So let's come to this, how to get the kth smallest value in a moment. But first, let's try to find how to get these count values, right? So what we can do is if I have, let's say 3, 1, 5, and some more values, I'll first sort my array A. And once this array is sorted, can anyone tell me how many times this value will appear in my triplet array? If let's say the size of array
56.
is what? Okay, someone is saying n+1. What about others? I think someone said 56, right?
N into n minus 1.
Okay, how did you came up with 56? Like, I don't know, maybe it's right. If you actually calculate this value, maybe it's 56. So anyway, and yeah, this is basically, see, you have n, apart from this, you have n minus 1 other indices, and if you select any of the two values from this index, and the third one is this, you're always going to get the minimum as this. So number of ways, let's say this n minus 1 is as x, so this is nothing but xc2. So n minus 1, what is xc2? Xc2 is nothing but x into x minus 1 by 2. So n minus 1 c2 is going to be n minus 1 into n minus 2 by 2. So if these are the total number of ways, let's say number of ways to select j, number of ways to select k. Is this, first of all, is this making sense? Whatever I'm doing. These are, you're getting this thing, right? Out of these n minus 1 indices, I need to select two other indices. If I select any of the two indices, I'll always, if this is my I and I have some j and k here, I'll always have this thing as my minimum. Why? Because I have sorted my array. And xc2 is nothing but x into x minus 1 by 2. Since I am finding n minus 1 c by 2, so this is the value that I'll get. Similarly, for each of the index, I have to do the same thing. Let's say I'm currently here, so I look at how many indices occur after this. Why? Because only, like, if I select, I have to select j and k from this side only. These are the only options that I have while selecting j and k. Because if my current element is I is here, and I try to choose any element from here, I won't get this as my minimum, right? Okay, so someone is asking why I have n minus 1 c2. So what do you mean by this? Like, how did I come up with this value? Okay, let's say, okay, you have this array A. Okay, these values are sorted, and I'm trying to find how many triplets there exist, how many, like, if I is fixed at this position, okay, how many ways there are to select j and k such that my minimum value of ai, aj, and ak is going to be equals to ai only. How many ways are there? And now, since my ai, this value is already sorted in increasing order, on, let's say, sorted in non-decreasing order, so I can select any of these. I can select any of these as my j. Once I select my j, then from that position I can select any of those values as my k. So technically, what we are doing, from n minus 1, we have to select any two values. Is that okay? Okay, someone said if we are selecting a single number, then the remaining elements are n minus 1. Yes. So is this a doubt? Yes, it's true. If we are select for this number, but if we are here, then these are the number of, then we don't have n minus 1. Rather, we have, let's say, whatever value this is. Out of these numbers, we have to select two numbers. So it's in that case, it's going to be something like n minus I minus 1. If I is starting from 0, all my values are 0 index, n minus I minus 1 C2. If you put I as 0, you'll get n minus 1 C2. So finally, for each of these values, you'll get what is the number of times that this value is going to appear. Okay. Okay, let me draw this again. So for each of the values in my array A, I'm going to get how many times this value appear in my, how many times this value is going to appear in my triplet array, how many times this is going to appear, how many times this is going to appear. And now finally, I have to find which is the kth smallest value. So what I can do is, so kth smallest value simply means that 1 is appearing 3 times, 2 is appearing, let's say again 3 times, 3 is appearing 2 times, and 4 is appearing 1 times. And let's say I have to find 7th smallest value. So first of all, this is appearing 3 times, this is appearing 3 times, this is appearing 2 times, this is appearing 1 time. So what I can do, I can first of all, now from this point, you can solve this problem in many ways. What I did is, you can calculate prefix sums, something like 3, 6, 8, and 9, and then apply binary search that at which position you first time you get a value, since you have to find the 7th value, right? So 7 will come somewhere in here, between here. Is like, am I making sense? So this value, that is the 3rd position value, because up till this point you had only 6 positions, and after this you had 8 elements in your triplet array. So whichever element is at this position, like this 3rd position, it is also the 7th position, like it is also the 7th smallest element in the triplet array. So you can just find which value is this, like which is the 3rd indexed value in your sorted array, and you can print it. Is this making sense? Yes, no, anything? Is it clear? Okay, it's not clear to some. Okay, it's clear to this, but it's not clear. See, what we did is, we had an array, we sorted it, and we counted how many times each of these values is going to appear. Let's say this is appearing 5 times, this is appearing 4 times, 4 times, 3, 3, 2, and 1. Okay, so this is the number of times my values, these, after sorting, these values are going to appear in my triplet array. So 5 times, if I take my I, j, k, and I find minimum of I, comma, j, comma, k, after I'm done with everything, this value is going to appear 5 times in my triplet array. This value is going to appear 4 times in my triplet array. Is this clear? Okay. So now I'm saying that I have to find which is the 10th value in my triplet array. This value is going to appear, these values are sorted in non-decreasing order, right? So I have to find 10th smallest array, 10th smallest value. So this value is going to appear 5 times, 1, 2, 3, 4, 5. This value is going to appear 4 times, 1, 2, 3, 4. And then this value is going to appear again 4 times, 1, 2, 3, 4. So I can look at, okay, 5, I want more, 4, I want more, 1. This is the 10th value. So how to get this value? One of the ways is calculate the prefix sum, 5, 9, 10, 5, 9, not 10, but 13, 16, 17, 18, 19, 21, and 22. And find the first position at which the prefix sum value is more than k. So this would mean that this element, or the value which is at this index in my array A, is going to be the kth smallest value, right? Is it clear now? Yes, no, anything? Okay, probably, yeah, searching linearly will give you TLE, but if you apply binary search, because after you have calculated, like once you have calculated prefix sum values, your array is non-decreasing. So if your array is non-decreasing, you can apply binary search on it.
We can directly use lower bound.
Yes, 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 yes. I have also, let's move to the implementation. Is it clear till now? Is it clear to everyone? Okay, so let's look at the implementation. So this is the implementation. In this, first I'm taking n as input. N is this number of elements in my array A. Q is the number of queries that I have to process. So I'm sorting my array A, and then these are the count, like the number of times my ith index value, count I is number of times my ith index value is going to appear in my triplet array. So x is nothing but n minus I minus 1, like we said, right? So I have to find this n minus I minus 1 C2. So first of all, I'm storing this value in x, and then I'm calculating xc2. So this is nothing but xc2. So this is my count I. Finally, I'm having prefix sum calculated. And once I have calculated my prefix sum, I'm finding the first position, which is either more than or equals to k. So lower bound gives me an iterator pointing to this positions. I'm subtracting this. From this, I'm subtracting my count dot begin so that I get the index. Once I get the index, I'm printing a of position. Is it clear? Yes, no, anything? Okay, what about?
Yes, it's clear.
Okay, so let's move to the third problem. So this is the third problem. In this problem, we are given that we have two integers n and k, and let s denote the smallest number of n digits such that no substring of s having length strictly greater than k is a palindrome. How many of you were able to solve this problem during the contest? Okay, so what, this is just an observation problem. So let's see what we have to find. So what we have to do, we have to find the sum of digits of a number, of a smallest number of size equals to n, whose, like if we see this number as a string, so any substring of size strictly more than k shouldn't be a palindrome. So first of all, is the problem statement clear? Is the problem statement clear to everyone? Okay, so the problem statement itself is not clear. See,
Do we have to make the sum as small as possible?
no, we don't have to make the sum as small as possible. We have to find the sum of digits of the smallest number of n digits, like which has n digits, and this number, let's say that this number is s. So any substring, like any consecutive k plus 1 digit shouldn't be palindrome. Like once you finally have a number of n digits, any of its consecutive k or k, like more than k digits, shouldn't be a palindrome. And you have to find the sum of this number, sum of digits of this number. You don't have to find that number, you don't have to minimize the sum, just you have to find the sum of the digits of this number. So is it clear? See, there are many numbers which have n digits, right? There are many numbers. Let's say my n is 5. So there are many 5-digit numbers, right? Out of all of these 5-digit numbers, you have to find the smallest number. Let's say my k is 2. So you have to find the smallest number, for which if I look at any, since k is 2, any 3 consecutive digits, these shouldn't be palindrome. Any of these, like if I just look at these 3, it shouldn't be like this 1 2 1. This is a palindrome, right? So these 3 digits shouldn't be a palindrome. Then 4 digits, like if I look at these 4 digits, they shouldn't be also a palindrome. And if I look at the whole number, which is at all the 5 digits at once, they shouldn't also make a palindrome if k is 2. So if k is 2, I'm looking at substrings which are strictly greater than k. Is it clear now? So out of all of these 5-digit numbers, I have to find smallest such number, and I don't actually have to find that number. I just have to print the sum of the digits of that number. So in a way, if you, yes,
Can we make this number using 0, 1, and 2?
yes. So what we need is, we actually, if we want sum only, if we want the sum of the digits, in a way we are finding that number only, but we cannot actually find that number literally and print it, because n is going up till 10 to the power 9, right? So see, since first of all, what should be at the first position? We want the lexicographically smallest number, and we cannot have a 0 at the first place, right? It's mentioned that it shouldn't have any leading zeros. So we'll have 1 here. And now I want the smallest number, and it's mentioned that I shouldn't have a palindrome of size more than k. So I can have a palindrome of size k, right? So let's have k zeros, because I want to make the smallest number. So these are k zeros. After this, what should I do? If I try to put because see, I'm trying to greedily put numbers, because finally my objective is not to make sum is smallest. I have to make this number as small as possible, right? So this one is anyway going to be here. Why? Because I need to make a smallest number, and I cannot have a 0 here. Then after that, let's have k zeros here. Then what should I put here? 0, 1. Can I put 0 here?
No.
If I put a 0 here, I will have k plus 1 zeros. They'll definitely form a palindrome, and I cannot have a 0 here. Can I put a 1 here?
No.
If I put a 1 here, then also we'll have a palindrome. So I'll put 2 here. What about here? What about these? What should I do?
1.
Why 1? Why not a 0? If my k is 5, why not a 0?
Yeah, 0 is 1.
Yeah, let's put k plus 1 by 2 zeros. Why k plus 1 by 2 zeros? Because those are the only number of zeros. After that, you'll have a palindrome like this. If let's say I have k is equals to 5, and first I put a 1, then 5 zeros, 1, 2, 3, 4, 5, then I put a 2. And what is k plus 1 by 2 for k is equals to 5? I have to put k plus 1 by 2 minus 1, because if exactly I put these many zeros, then also I'll have a palindrome. Let's see, if I put 2 zeros, am I getting a palindrome of size 6?
No.
Because if k is 5, I'm looking for palindromes which have length more than 5. So right now I don't have a palindrome of size 6. But if I put a 1 more 0 here, then I'll have a palindrome of size 7. This thing. So therefore, k plus 1 by 2 minus 1 is the number of zeros that I can put after this 2. Okay, let's look at this was for this case when I had k is odd. Let's make k even. So k is 6. So then also you'll see that this approach works, because 1, then 6 zeros, 1, 2, 3, 4, 5, 6, then 2. And then I'm saying k plus 1 by 2 minus 1. So k plus 1, this is 6 plus 1, 7 by 2. It's 3 minus 1, 2. Right? If I put one more 0 here, then again I'll have 7. I'll have a palindrome of length 7. So in any way, I can, so what we are doing, first we are putting 1, then we are putting k zeros in our final number. Then we are going to substitute 2 here. And then we are going to have k plus 1 by 2 minus 1 zeros here. What do we need to do after that? So this thing is done, like some 1, we have a 1, then we have, let's say, k zeros. So we have k zeros, then we have a 2, then we have k plus 1 by 2 minus 1 zeros. What do we do after this? We cannot have a 0 by, because if you have a 0, we have already seen that these are the maximum number of zeros that I can have. So what do we do after this?
We can put 1.
Yes, why not 2? Because both 1 and 2 are valid for this position. No, actually 2 is not valid. Why? Because
We want smaller number.
yes. So I'll have a 1, and then after this position, I'll follow the same approach afterwards. Right? So this kind of thing will keep on recursively getting, like, substituting these digits till I reach n. So let's look at this 1 unit of block size. In this 1 unit of block size, the size is 1 plus k plus 1 plus, in case I have my k as 0, so I'm going to write this as maximum of 0, or k plus 1 by 2 minus 1. This, if my k is, like, actually I don't have to write maximum 0 by, because my k is more than or equals to 1. So if my k is more than or equals to 1, this value is always going to be at least more than or equals to 1. So this value is going to be more than or equals to 0. So finally, I have something like, this is the length of my block, this 1 unit block. Let's call it a unit block. These blocks will keep on following. Like, this is the same block that I'll have here also till, and these blocks will keep on getting added to my final number till I reach length n. It's possible that at the final block is not included completely, but it's a portion of it is there. So I have k plus 1 by 2 minus 1, right? This is the length of my block. So let's remove this. I have something like k plus 1 plus k plus 1 by 2. Now there's one more thing. How to actually count how many ones we are getting. So we can simply count, this is the, let's call this as divisor. This is the length of my block. And what I can do, I can count ceil of n by this divisor. These many times I'll get 1. Is this making sense? Like, these are all the blocks, right? And in each of these blocks, I'm having a 1 here. Right? So I have to count the sum of my digits. So I'm counting how many times I'll get 1. So these are the number of times that I'll get 1. N divided by the length of this block. Is this clear? Is it clear? Yes. Okay. Okay, someone said no. What isn't clear in this part? Okay, you'll have to explain, right? Which part isn't clear? Okay, either unmute yourself. Okay, I am clear about the place 1 and 2, but how to calculate? Yeah, we are looking at the calculation part. See, since after we are trying to find, okay, this is the block which is going to get repeated again and again, right? After this position, we are again going to have this 1 at this place, and then again we are going to have k zeros, then a 2, and then k plus 1 by 2 minus 1 zeros. And then again, the same thing is going to follow. So let's say that this is a block that is going to repeat again and again, and the length of this block is this thing. The length of this block is this thing. And in this block, I'm going to have a 1 one time and a 2 also one time. But let's forget about 2s. Let's just look at 1s. So how many total number of 1s that I'm getting? It's n, that is the total ceil, divided by how many blocks I'm getting. Ceil of, because 1 is appearing at the front. If I'm having 1.5 blocks, I'll get 2 1s. Why? Because 1 is appearing at the front of these blocks, right? If this block is having just only one element also, then also I'm getting 2 ones. K plus 1 is the length of the first block. K plus 1 plus K plus 1 by 2. This is the length of the block. So first of all, is this clear why we are taking C? Someone asked why we are taking seal. Is it clear why we are taking seal? Because if I have 1.5 blocks, I'll have 2 ones. Okay, so this is clear. So this way, n divided by seal of n divided by that div value is going to give me number of ones. Now, how to get number of twos? So for getting number of twos, see, we have 1, then we have k zeros, then we have a 2, then we have k plus 1 by 2 minus 1 zeros, and then this thing is going to repeat itself, 1 and then k zeros, and then again 2. So let's look how many. Let's remove this from my final number. Let's remove these k plus 1 digits from my number, k zeros, and this 1 digit from my number, and let's start from here. So again, if you see, if I make a block of this thing, then again this is having how much size? This is 1 plus k plus 1 by 2 minus 1, then there is this one plus 1, and then again k zeros, so plus k. So again it is nothing but k plus 1 plus k plus 1 by 2, which is same as the earlier div value. But now if I remove this value, then I have this block, and again I have 2 at my starting, and in each block I only have 1 2. So I can count number of 2s as n minus k plus 1 divided by this div value, take it seal. These are the number of 2s that I'm going to get, multiply this by 2. Why? Because I have to find the sum, right? Add this to your answer. Is it clear?
Can you explain the last part again?
Which part?
Why we are dividing by div and subtracting n minus k plus 1? That part.
Like earlier we made some blocks, and in that block one was appearing, like you don't have to actually do this if you're able to find another pattern, but this is one of the ways to calculate. I had 1 in starting of each of these blocks. So what we were saying, that let's find how many blocks are going to get required for this, for making this n size number. So these are the number of blocks. Let's say this is 3.5. So number of one, like the number of ones is, 1 digit is going to come 4 times, because 1 is appearing at the front of these blocks. So even if I'm taking just 1 character or 1 digit from the last block, then also I'm going to get 1. So similarly, if I remove the k plus 1 digits from starting of my number, so I have k zeros and 1 at my starting. If I remove these and only look at this part, I'll have 2 at my starting, right?
Yes.
And then again, these are the same blocks, but in these blocks, it's just that they have 2 at the starting, and the size of these block is again that same div, which was k plus 1 plus k plus 1 by 2. So now I can say how many times n is the total number of digits in my number minus these. I'm removing these digits, so these are k plus 1. So this gives me only this part. Divide this by div. So this gives me how many blocks will be required. And once I get this part, this is the number of 2s that I'll have. Basically, this is the number of blocks I'll have. Let's say this is 2.5, the seal of it is 3. So I'll have 3 2s, and I need to multiply this with 2. Why? Because if 2 is occurring 2 times, the final sum is going to be 4. 2 times 2, right? So is it clear now?
Yeah.
Okay, what about others? Okay, either write in the chat, yes, no, something. Okay, which part you didn't understand? This n minus k plus 1, right? You can unmute yourself.
Okay, so we started from 2, so making similar blocks throughout.
Yes.
So that's why we are subtracting k plus 1 from it and again dividing by div.
Yes. This k denotes those k zeros, and this
And
one
one
denotes
we put at starting.
Yes.
Okay.
So once we remove this, we'll have our block starting from 2.
Okay, sir. Got it.
So let's look at the implementation. So this is the implementation. This CL function is nothing but giving me CL of A divided by B. So you don't actually have to implement this. You can use CL, that inbuilt function, or you can do this simply here also. So I don't think that we are required to do this. Okay. And let's have just this as 1. Right. So now what we are doing, we are taking n and k as input. Initially, I'm initializing my answer as 0. This is just to calculate CL of A divided by B. And this div value is k plus 1 plus k plus 1 by 2. So I'm calculating first of all CL of n divided by this div. And then I'm adding 2 into CL of maximum. You'll have to take maximum because there is a possible case that n is less than k plus 1. You don't have those many. You don't have to form those many digit number. So you take maximum of n minus k plus 1 and 0 and divide it by div and take CL of it.
But a is always greater than k.
Yes, okay, so I didn't look at it, so probably this would also work. And this should also work. Is it clear? Like actually I was writing max, or as I remember during the context, I wrote max here also. Because maybe I read that problem statement only once, and instead of looking at those input constraints, I just like implemented it for a general case. So, but yeah, if n is more than if k is always less than n, so then you're going to have this thing. Is it clear? N, like what we were having, n minus k minus 1. Is it clear? Yes, no, anything?
One doubt I have.
Yes.
When we are taking the seal, we take seal by adding then plus 1 by something.
No,
Why
no,
were
no.
minus?
This is how you take seal.
Okay.
Like I said, you don't have,
Why does the seal function doesn't work? Seal function.
it works. Why won't it work? You can use seal function. Like I have a habit of implementing this, so but seal function works. You don't have to use seal function. Like you don't actually have to use your hard-coded seal function. You can use inbuilt library seal function also. Just make sure that you're giving it double values. Don't pass integer values to that function. Okay. So let's move to the fourth problem. So this is the fourth problem. In this problem, we are given that we have a permutation of size n, and we are given that we can a good number so we are given a permutation of size n, and an integer x is said to be good if after performing the following operations on the permutation exactly once, we have a special permutation. So special permutation is nothing but if we have n integers, if we sort those n integers, those n values should be consecutive to each other. Those n values should be consecutive n integers. Let's say 4, 5, 6 is a special permutation. 9, 10, 11 is a special permutation. 9, 10, 13 is not a special permutation. So if this was 17, 18, 19 is a special permutation. So all the numbers should be consecutive. Once sorted, they should be consecutive to each other. So we are given that we have to apply XOR with each of these elements, and X is said to be a good integer if after doing these XOR operations, my final, like initially I had a permutation of 1 to n of size n. So afterwards, I'll have a special permutation. So what we need is, initially I had something like 1, 2, 3, 4, 5, 6, 7, 8. Let's say I had 8, a permutation of size 8, and my L is 5. And okay, let's take example input only. So in my first example input, I have a permutation of size 3. So I have a permutation 1, 2, 3, and then I have Q queries. So the first query is for the first query, I'm given my L as 1 and R as 3. So L is 1 and R is 3. So this means I have to find number of good integers between this range. So how to find a good integer? There is a good integer 3, and why is 3 a good integer? Because if I perform my XOR with 3 XOR with all of these elements, 3 XOR 1 is 2, 3 XOR 2 is 1, 3 XOR 3 is 0. So all these numbers, if I write them in a sorted manner, they will give me 0, 1, and 2, and these are occurring in a consecutive manner. So that's why this is a special permutation. So if this is a special permutation, since I chose X is equals to 3, so this 3 is a good integer. So finally, I have to count how many good integers are there. So first of all, is this clear? Like, what is the problem statement asking me to do? Is it clear or is it not clear? It's clear, right? Okay. So, like, I'm gonna first claim something. My claim is all the good integers X will, if let's say n is having something like, in the binary representation, n is something like 1, 0, 1, 0, 1. So this is the most significant bit, right? So for all of these bits, from 0th bit to most significant bit, either all of these bits are going to be 0 in my X, or these bits are going to be 1 in my X. We are not worrying about all the bits that are going to appear in front of these most significant bit of n, but all of these bits will either be 0 or 1. Why? Now let's prove it. Why? So the proof is, like first, let's see what happens if I select 0. If all of these bits are 0 and I have something here, so if I have some ones here, so this is nothing but, let's say, saying that let's say this is ith bit, this is jth bit. So I'm adding 2 to the power ith and 2 to the power jth. Let's call 2 to the power I plus 2 to the power j something as alpha. So I'm adding alpha because all of these bits are 0. They won't change any of the bits in my original n permutation array, right? A permutation of array n had only all of those elements had bits open among these bits only, because this is the most significant bit in n. So if I have only zeros among these bits won't get changed. For ith, like for all of the elements, I'll just add alpha. Alpha is this thing. If I had I and j bit open in my X, so all of the elements will just get incremented by alpha. So if I had something like 1, 2, 3, 4 earlier, I will have alpha plus 1, alpha plus 2, alpha plus 3, and alpha plus 4 finally, right? So x equals to 0 works, right? X, like this thing works. Is this clear why this thing works if I have only zeros? Okay, so now let's consider when I only have ones. So if I only have one, my one, if I take XOR from with one XOR this number, like if I only have ones, forget about these bits. Okay, let's say these bits are right now they are only 0. So one XOR this kind of x will give me x minus 1. Why? Because if all the bits are open, I'm closing this bit. If I have these two, I'm closing these two bits. If I have everything open, I'm closing everything. So 1 XOR x in this scenario will give me x minus 1. So if I had something like 1 to n, and this will become x minus 1, this will become x minus 2, finally x minus n. So these are also consecutive, right? So both of these work. What about anything between these two? So they won't work. Why? Let's see. If I have something having x is between 0 to 2 to the power k minus 1. X is between these two. I'm not worrying about the bits which are bigger than most significant bit of n, but let's not worry about them right now because they won't actually have any difference on the final values. All the final values will just have alpha added because of them. So I'm not considering them right now. I'm just considering these bits which are less than or equals to most significant bit of n. So if x is between these, answer doesn't exist. Why? See, if x is between these, I have something like 1 to till n, and I'm having x XORed with these. So let's break this into two parts. First of all, when my x is between 0 and 2 to the power k, like k is my most significant bit. Okay, here k is my most significant bit. So let's break this into two parts. How to prove that any of these is invalid? So first of all, x is between 0 and 2 to the power k minus 1. And in second scenario, let's say x is 2 to the power between 2 to the power k minus 1 and 2 to the power k minus 1. Right? So if x is between these, it would mean my x is less than n. Why? Because n had this 2 to the power k minus, like this bit was open. This is the max. This is like most significant bit in n. So this was open in n. So if my value is less than or equals to 2 to the power k minus 1, that means that x is less than or equals to n. So if x is less than or equals to n, I have something like this till n. I choose 3. So first of all, I'm going to get 0. I'm definitely going to get 0, right? In this case. So if I'm going to get 0, that means that all the numbers should be between 0 to n minus 1, and each of these numbers should be appearing exactly once. But since I'm doing XOR with 3, I won't actually get 3 here. Why? Because in order to get 3, I should have something like 0 here. Then only 3 XOR 0 will only give me 3. Other than that, it's not possible to get 3. So, and since in the original permutation, I don't have a 0, so 3 will be missing in this permutation. So in this case, this is not valid if x is between 0 and 2 to the power k minus 1. So what about if my x is between 2 to the power k minus 1 and 2 to the power k minus 1? This is also the same. If I have something like this, I'll always get this thing, which has most significant. This is the most significant bit, that is the k bit. I'll always get something like this. Why? Why will I always get something like this? Because I'm using something like 1 1 1, and let's say this is the most significant bit and I'm using this thing. So since this is the most significant bit in n, there will always be a number like this in my original permutation. So if I do XOR with this, I'll get all the ones. So if I have this number, this would mean that all the n numbers should be consecutive to this, right? But again, if you see x is somewhere here and I cannot get x because for that there should have been a 0 in order for me to get an x, and 0 is simply not present in my original permutation. So that's why both of these cases are not valid. The only valid cases are all the bits from most significant bit to 0th bit, either they should be 0 or all the bits should be 1. Now, how to find how many numbers are there between L and R who have the last, let's call these k bits, these most significant bits as k bits, most significant bits in n as k bits, all of these bits, how many numbers are there that have all of these bits as 0? So if I have k is equals to 5, I'm talking about all the numbers which have 5 zeros, and then there is something like this, maybe 1 0 1. There are some bits here, but all of these 5 bits are closed. So this is nothing but we can actually find this by doing r, just divide it, right? 2 to the power k. Why 2 to the power k? This is similar to just see how many multiples of the, like if I have to find, okay, between 10 to 20, how many multiples of 3 are there? So what will you do? You will do something like 20 divided by 3 minus 10 divided by 3, right? You'll do something like this, right? So that is what we are doing here. So we are doing r divided by k, and then we'll remove L divided by 2 to the power k. And since it can actually be included, like L and R are inclusive, both the endpoints of the range are inclusive. So I'll do L minus 1 divided by, here also you won't actually do 10 by 3, but you'll do 10 minus 1 by 3, because there's a possibility that this number is actually divisible by, like this actually contributes to a final x. So I'll have something like L minus 1 by k. Is this clear? I know this is like not that easy to imagine if you're not good with these bit set theory. But once you get the idea that the last k digit should either be 0 or the last k digit should be 1, then these are the number of possible ways if to get a number if you have the last k digits as closed, and how to see for open. If the last if your last k digits are open, you can see that if x is a number who has last k digits open, x should be divisible by, x plus 1 should be divisible by 2 to the power k. Why? Because if you add 1 to this number, you'll have this bit open, and this is nothing but kth bit, k plus 1 in bit. So this is 2 to the power k plus 1. 2 to the power k, not k plus 1. Right? So just check that how many x plus 1. So instead of checking for x plus 1, we can simply check for L plus 1, how many numbers are there between L plus 1 and R plus 1, which are divisible by 2 to the power k. So first add your answer. Answer plus equals to R divided by 2 to the power k. K is the most significant bit in n, and L minus 1 divided by 2 to the power k, and then add R plus 1 divided by 2 to the power k minus L minus 1 plus 1. So it's nothing but L divided by 2 to the power k. So if you add these to your answer, you'll get your final answer. And the implementation is also like quite easy only. Like this is the implementation for this problem. So max bit is nothing but the most significant bit in n, and once you have got that, so 2 to the power most significant bit. So if I have fifth most five significant bit, I'm calculating 2 to the power k plus 1, because that's the next bit which I'm going to divide by. See, here, if I have to divide, if I have to check, okay, these 5 bits should be open. So I have to divide by 2 to the power this bit, right? This is what we were doing here also. So what is this? If this is k, these are the, this is 0, 1, 2, 3, 4, this is 5. So 2 to the power 5. So once this is done, I'm calculating power of 2, and from L to R, calculate this RR, or let's call this as, okay, call it anything, but you don't actually have to save these values also. You can directly put these values in this equation, and we'll get this as R divided by 2 to the power max bit plus, which is k, and L minus 1 divided by 2 to the power k, or 2 to the power max bit plus 1. Then once this is done, add this RR is nothing but R plus 1, as this is like, these was for all the last bits are 0, all the k bits, last k bits are 0, and this is for all the last k bits are 1. So if last all k bits are 1, then x plus 1 should be divisible by power of 2, 2 to the power k, and 2 to the power k is nothing but 2 to the power max bit plus 1. So instead of doing x plus 1, looking for x plus 1, let's find x is in R plus 1 to L plus 1 range. Because if x is in R plus 1 to L plus 1 range, then x plus 1 is in, like, if instead of, see, if my last k bits are 1, I add 1 to this, you'll find that this number is always going to get divisible by, if these are k, like if this is max most significant bit, these are most significant bit, this is the most significant bit. So if you add 1 to this, this will give you k. So this number will, if x is this thing, this kind of number, my x plus 1 will always be divisible by 2 to the power k, right? So instead of finding these x plus 1s, we are finding this, how many numbers are divisible in L plus 1 to R plus 1. Then let's say I find some number y, this y is going to be my, this x plus 1. So I can actually substitute, instead of, like, what will be the number? It will be y minus 1. And since I have found in range this thing, if I subtract this minus 1 from my range, I'll get my original range, right? LR. So that's why we are finding, instead of finding x plus 1, we are finding in range simply in L plus 1 to R plus 1 range. So this can be solved in many ways. You don't actually have to follow this mathematical approach. Once you, like, the only thing is you just have to observe that the last k bits should be either all 1 or all zeros. After that, it's just division. So after dividing these ranges with 2 to the power k, I'm adding these in my answer, and finally outputting, printing the maximum, either 0 or answer. Answer can be, like, there's a possibility that answer turns out to be negative if this temple is more than RR, or if here temple is more than RR. So is this clear? Is it clear? Yes, no, anything? Okay, so calculation part is confusing. See, you'll have to imagine those bits, otherwise it will be really hard. And I think there should be other ways to do this also, but they won't be quite like straightforward like this. But yeah, they'll be more convincing. If we are doing like this, I know that this is completely not convincing, first of all, and also this is quite confusing why we are dividing those numbers, right? So actually you can look at to this. See, if all the digits are 0 here, how many, after how many numbers will a number again, if I have something number, some bits here, after how many numbers again will all the digits be 0 again? You can look at like this, right? So this is nothing but 2 to the power k, where k is this bit. So after exactly these many numbers, again all of these bits will be 0. before it, there will be 1 here, then there will be a 1 here, then there will be a 1 here. But after exactly 2 to the power k numbers, I'll again have all these bits as 0. So that's why I'm dividing here 2 to the power 2 to the power k. Now, why I'm dividing by 2 to the power k when I have to look for only 1, like all the bits should be 1. You can again see that after 2 to the power k, all these bits will be 1. Or you can also look at it, if you add 1 to this bit, all of these bits will be 0, and there will be a 1 here. So this number is having only zeros in this part and 1 here for this bit. So x plus 1 should be divisible by 2 to the power k. Is it clear? Okay, it's clear. So we'll stop now, and thanks for joining. Bye. Good night.